What's up, people? How's it going? Welcome to my channel Secrets. So yesterday, I attended the GFG's weekly contest, which turned out to be pretty simple. So GFG conducts a weekly contest on every Sunday, and it usually contains 3 problems, which are to be solved in 1.5 hours. So without any further ado, let's get started with discussing the solutions for the problem. So in the first problem, we have n dishes with varying prices, and each dish is disliked by exactly one of difference. Right? So we'll be given two arrays, which are prices and dislikes. And prices array is nothing but it's the price of the ith dish, and dislike array means that the ith person will be disliking the dislike of I. So we want to find the minimum price of the dishes such that everyone gets at least one dish to eat, right? So this is a very greedy problem. So whenever we have something like minimizing the cost, we will first try to think greedily. So can we always include the dish which has the minimum price? So here 5 is the minimum price, and the dish is the third dish. So the third person is disliking the third dish. Now, other than third person, everyone is satisfied with that particular dish, right? So one has something to eat, two has something to eat, even 4 and 5 has something to eat. Now we just need to satisfy the third person. So now think greedily again. Now among all the dishes which are not disliked by 3, take out the minimum dish. That's it. So what are the dishes which are not disliked by 3? So 1, 2, 4 and 5. So these are the dishes which are not disliked by 3. So take out the minimum price among all those dishes. We'll be taking minimum of 10, 8, 12, 8, which is absolutely 8. So we'll be returning the answer as 5, which is the minimum element, and as it is disliked by 3, so we'll be trying to satisfy the 3 with another minimum element. So we'll be scanning the entire array and take out the price which is not disliked by the third person, right? So it will be turning out to be 8. So we'll be returning 5 plus 8. Now in this case, all the elements are 1. So in that case, we'll be returning minus as the answer. So this is a very simple problem. So we'll be scanning 2 times. So at first we'll be taking out the minimum element and its corresponding index. And in the second loop, we'll be finding out the minimum value of the dish which is not disliked by this person who has got the minimum price. That's it. So if dislike of I is not equals to dislike of the index of the minimum element, so I'll be taking that into consideration. So I'll be taking the minimum element among all those dishes. So if m12 is equals to int max, then it means that all the elements are equal, like in this case. So I'll be returning -1. Otherwise, I'll be returning m1 plus m2. So this is how we can solve the first problem. Now let's move on to the next problem. So in this problem, we'll be given a tree, and each node is having a weight of I. First node will be having a weight of 1. Second node has a weight of 2, and so on. Now we have to exactly remove one of the edges. So by removing one of the edge, the tree will be divided into 2 components, right? So among all those components, we have to take the minimum difference of the first component and second component. When we remove one edge, the tree is divided into 2 components. Let's say the sum of the first component is S1, the second is S2. Now we have to minimize the difference, absolute difference between S1 and S2. So that's what the problem is all about. Now let's say we have a graph like this. Now let's say we want to remove one of the edges which are associated with a leaf node, because that's the easiest edge to remove, right? So if you want to remove this edge, then we'll be getting 2 components, with one as the leaf node and the other elements will be in a separate component, right? So what is the sum of all the elements in this particular component? So it's only the leaf node, right? So the element will be 5, that is, the sum will be 5. So as ith node is having the weight as I, so we can easily predict the sum of all the edges, right? So if for n edges, will be having total sum of n into n plus 1 by 2. Okay, so we are having 5 edges over here, so it will be 5 into 6 by 2, which is 15 in this case. So the total sum of all the edges will be 15. So if one component has 5 as the sum, then the other component should be having 15 minus 5, which is 10, right? So this component will be having their sum as 10. Hence, after getting these 2 sums, we'll be taking the absolute difference. So let's say we want to remove this particular edge. So if you want to remove this edge, we should be able to somehow calculate the sum of all the elements in the subgraph with 3 as the root, right? So if you instantly calculate that, then we can easily predict the sum of the other component. So let's say we somehow get the sum 8, right? 8 is nothing but it's the sum of all the elements in this particular component. Then the other component sum will be 15 minus 8, that is 7. There is 1 plus 2 plus 4, which is 7. In this problem, the main task is to find out the sum of all the elements in a subgraph with ith node as the root. So we'll always scan from the leaf node because it's very easy to predict the sums of leaf node. So now for every node, calculate the sum of all the elements in the subgraph with that particular node as the root node. So for 2 as the root node, the sum will be 2 because it's a leaf node, right? So first calculate the sums of leaf nodes. Now go to one step ahead and calculate the sum of all those nodes. So the other step is nothing but it's the node which has the element as 3, right? Now for 3 should be having the sum of all the nodes in the subgraph with 3 as the root node, right? So the sum will be 3 plus the sum of all its subgraphs. So the sum that is stored with 3 will be 3 plus 5, that is 8. So till 3 the sum is 8. Now go to the next step, which is having 1 as the element. Now for 1, the sum should be 1 plus the sum of all the subgraphs, that is 2 plus 8 plus 4. So we should not be including 8 plus 5 because this 8 already includes the element of 5 in it. So 1 will be having 1 plus 2 plus 8 plus 4, which is ultimately 1 plus 14, that is 15. And it is exactly matching with the total sum that we got, right? So the first task is to predict the sum of all the nodes in the subgraph with that particular node as the root node. Now say we want to erase this particular edge. So for that we'll be taking out this component, right? Now as we know the sum of all the nodes below 3, so we can easily predict the sum of the other component. So the other component will be 15 minus 8, which is 7. So we'll be having the two sums with us. So we'll be taking out the minimum as absolute difference of 8 minus 7. We should be minimizing this particular difference. Now let's discuss the code for this problem. So at first I'll be constructing one adjacency list with the edges given in this problem. And in addition to that, I'll be maintaining another vector which is for calculating the degrees. So 1 will be having a degree of 3, 2 will be having an degree of 1, and even 3 and 4 will be having a degree of 1. And why I'm maintaining these degrees? Because it will be easy for me to find the leaf nodes and then the nodes which have the degree as 1. So as we had to calculate the answers from the leaf node, so the leaf node will be having the in degree as only 1, right? So if the in degree is 1, then I'll be pushing that into a queue, and initially all these nodes will be leaf nodes. And as given in the problem statement, so weight of the ith node will be I. So I'm assigning value of I as I. Now I'll be scanning through the elements of the queue, right? So initially the queue will be containing the leaf nodes, and then I have assigned the initial values to all the nodes over here, right? So after popping out, I will be first calculating the answer with having a subgraph with ith node as the root node. Now ND is the node which is popped out of the queue. So ND is the node which will act as the new root. So what I'm trying to mean is that, so when this is the leaf node, so if I pop this element out, then 5 will become the root node. I know the sum 5. So with that I can easily calculate 15 minus 5, which is the sum of the other component. So the difference will be nothing but it's sum minus, so sum is n into n minus 1 by 2, sum minus the value of nd minus value of the node. So it's nothing but it's sum of 2 times the value of the node, and we want to minimize the this particular difference. Now let's say we have gone through this element. Now at this scenario, the node 1 will be having the in degree as 3, right? Once the answer for 2 is computed, so I'll be decrementing the in degree of 1 as 2, so that in future the node 1 can be pushed into the queue once the in degree of 1 is equals to 1. So I'll be going through all the adjacent nodes of ND, and I'll be decrementing the in degree. So if this in degree is equals to 1, then I'll be pushing that into the queue. And as I discussed with you over here, so if I come to the node 3, then I'll be including sum of all its subgraphs, right? So I should be adding the value of node into value of IT. And this will be done until the queue is empty. So I'm just taking out the nodes which have the in degree as 1, and I'm calculating the answer for that. And now after that, I'm going to the adjacent nodes and then decrease in the in degree, and the in degree is 1, then I am pushing that into the queue. So while I'm pushing that, I'm also calculating the value of all the subgraphs with that particular node as the root node. That's it. So this is the entire code for this problem. Let's move on to the third problem. The third problem is a DB problem. So in this, we'll be given n switches, and this is a binary string. So we'll be having 0, and 0 indicates off state and 1 indicates the on state. Now we'll be given another array which is cost, and it will be of the size m. Okay. Now we can take I contiguous elements and turn those elements into 1, and it will be costing us costs of I. Now we want to determine the minimum cost to make all the elements as 1. Now just look at the constraints for this problem. So n is given as 10 power 5, and the maximum value of m can go up to 100. Now this can be solved easily in a time complexity of big O of n into m. For every index, try to go through all the possibility of the cost array. So what I'm trying to mean is, we'll be constructing a DP, and DP of I will mean that it will be having the minimum cost of making all the elements till the ith index as 1. Right. So this is how I'll be defining the state of DP. So DP of I will be having the minimum cost of making all the elements till the ith index as 1. So let's say I want to calculate the answer for the 7th index. So what is the cost of just taking out one contiguous element? So it is 1. So if you just take one contiguous element, then the cost will be 1 plus the minimum cost of making all the elements till the 6th index as 1s. That is, I'm having m elements, and m is the maximum limit for taking contiguous elements, right? So I'll go through all the possibilities of m. So now I iterate from all j from 1 to m. So j is the length that we have. So for every length, calculate the dp of I. So how to calculate the dp of I for every length? So for the 7th index, if I'm taking 3 contiguous elements, then it will be having a cost of 8, right? So if I take 3 contiguous elements, then what is the index which comes after taking the 3 elements? So 7. So if I take till 7, 6, and 5 will be taken out, right? So the cost will be 8 plus dp of 4, because 5, 6, and 7 are taken out while taking 3 contiguous elements. So if I take j elements, then I'll be considering the cost of j plus dp of I minus j. So for every I from 0 to n, we'll be trying to go through all the j from 1 to m. So we'll be trying to compute the cost by taking j contiguous elements, and this should be minimized, right? So I'll be taking the minimum cost among all these contiguous costs that I'm getting. So this is how we'll be solving this problem. Now let's quickly move on to the code. Going through all the elements from 0 to n. So at first I'll be assigning a maximum value to dp of I. So whenever we are taking minimum, we'll be assigning a maximum value, and whenever we are maximizing, we'll be assigning a minimum value, right? So dp of I will now be 10 to the power of 15. So if the element is 1, then it's already turned on, right? So we will not turn it again. So the dp of I will be nothing but it's dp of I minus 1. If f of I is 0, then I'll be going through all the possible contiguous lengths, that is from 0 till m, and then I'll be taking out the minimum cost among all those elements. And also I'm considering cases like for the second element, I can also take contiguous 6 elements. And why am I taking it? It's obvious that m will definitely be less than or equals to n, right? So somewhere in the future, I'll definitely be getting a case when I can include all the 6 elements. So there, I'll be assigning the value of 6. So there is nothing wrong taking contiguous 6 elements for the second index itself. So at last, I'll be returning the value of dp of n minus 1, which is nothing but it's the minimum value to make all the elements as 1 till the n minus 1th index. So this is how we'll be solving the third problem. So these are the 3 different problems that we had for this time's weekly contest. And I can very well say that the problems are towards the easier side. So that's it for this video, guys, and thanks for watching.